Hello, this is the fourth part of Lecture 21 review of Eigenvalues and Eigenvectors. And there's only two more left to discuss here in this chapter, which are the determinant and trace and the eigenvalues for a plus b and a times b. And let's bring out our previous example of a equals to this matrix. And then we say we solve it by computing the determinant of a times lambda identity. So this will bring us into this form. And then we get this. And then we get minus 6 lambda plus 9 minus 1. So you have this form, and then we can factor out. We have lambda 1 of 1 and lambda 2 of 2, right? Yes. Let me bring that out here. And the trace and determinant is just another way to like verify if we get those lambda correctly. So notice that lambda 1 plus lambda 2 is equal to 6. And how do you get 6 here is by summing up the terms in the diagonal, and this is called the trace. And that's a new terminology, and you should remember it. So when we're talking about the trace of a matrix, we are interested in the diagonal component of it. Okay, so the trace of A, usually it's even shortened to A. The TR of A is equal to the sum of the lambda. Okay, and there's another thing, which is the determinant. So what is the determinant of this is 9 minus 1. So you have 8. And where do you see this number? Exactly, you multiply this. So the determinant, the det of A is, I would call this the big pi, which is the multiplication of the lambda. Okay, so this is like lambda 1 times lambda 2 times lambda n and so forth. And this is in green is the summation of the lambda. So these are the two things that I want to discuss in this point, the trace and the determinant. And only a small comment here, even the 2 by 2 case is really nice because this those trace and determinant also come out here. You see this 6, this minus 6 is this 6 is actually the trace, and this 8 is that determinant, and you just need to add the minus here. That's a small comment. And we move on to the next one. The next one and the last part is the eigenvalue for a plus b and a times b. So let's say I have a matrix A with the eigenvalues of lambda and matrix B with eigenvalues of beta x. And is this a correct way to get the determinant of a plus b? The answer is no. Why is that? Because this is where the problem happens, because there's no way to guarantee that x eigenvector is the eigenvector of b. So how to compute the determinant or the eigenvector or eigenvalues of a plus b? So you ask how to compute those. Well, you have to follow the same process again by doing the determinant and finding the eigenvector for each eigenvalues. And also the same case happened for the determinant of the multiplication between them. So let me just write it clear that it's not the case here. And also this is not the case of this. So imagine AB times X, some eigenvector is equal to A times, if I have the BX here, I'm sorry, I need to add x here. Bx here is the beta x, and then if I switch up the beta, and then you have the beta ax, and then you have the beta lambda x. And this is actually also not true, with the same reason that there is no reason to guarantee that x is also the eigenvector of b and a. And the book mentioned the only condition that this is true, so if only x is the eigenvector of a and also the eigenvector of b, then this will be the case, and also this will be valid. B times a eigenvector equal to this as well. So all the eigenvector shared, then we can multiply the eigenvalue. So this is the final concept that I want to tell you. So remember the determinant and trace of the matrix, and the trace is the summation of the eigenvalues, and the determinant is the multiplication, the product of the eigenvalues. And the case where the eigenvalue and eigenvector for matrix, two different matrix, summation of two different matrix, and the products of two different matrix. Remember what case that one theory might be invalid. And yep, that's it for this review. So let me know if there's any mistake. Thank you. Goodbye.